what we want to do today is to sort of wrap up at least this introduction to sequences and series that we started in the last session or two. And what we're going to focus on today is something called geometric sequences and the behavior of those in the sense of what you've previously studied is similar to your exponential background. And then we also want to talk about the geometric series, which is when you then do what with a group of terms in a sequence. You're adding them together, and that's what we call series, okay? And we're trying to familiarize you with what we call sigma notation or summation notation, so that when you see this in other courses, you'll at least have an introduction to it, and then you can sort of move on from there. So what we talked about in the last session, I want to do a quick summary of the arithmetic sequences in series. And what I'd like you to keep in your head is that an arithmetic sequence behaves like what in algebra? What type of function? Linear. Okay. So those things are behaving in a linear type of fashion. And then when you start adding the terms together, at the close of the last session, I showed you a little something in algebra that appeared kind of confusing because it was just all symbols. But when you start adding the terms of that linear progression, that linear sequence of values, when you add those values together, forming that series, arithmetic series, then the behavior of that is not exponential, quadratic. It's quadratic in its behavior. If you took notes or you watched the DVD or video from the last session, you'll see in the algebra structure there that it becomes quadratic in the variable n squared kind of term showing up. Okay, and I showed you an example of that. Okay, so the formulas, here were the formulas that we had from these arithmetic sequences. Here's the nth term of an arithmetic sequence. The nth term is the way we describe that, and it's equal to the value of the first term plus the term number you're on, take away 1, times the common difference. The common difference essentially is the slope that you saw back when you studied linear functions. All right? The slope. Okay. The group of terms, each term is going to change by a value of d as you move from one term to the next. So if d was a 3, then that means as you move from the first term's value, maybe it was a 20, then the next term is going to be 23, 26, 29, okay? And then when you add a group of those terms together, we get a partial sum, is what we call it. A partial sum of the first n terms, and most textbooks will use a capital S with a subscript n, and that means partial sum of that you're adding up the first n terms. And here's the sigma notation or summation notation, where your index starts with k equal to 1. Oh, and I made a little mistake right here. This should be a subscript k, because this is our index or our counter. So we start with k equal to 1, and then we're going to then add this sigma character means add terms together. So we're going to start with k equal to 1. So we're going to have the first term a sub 1, and we're going to add to it. Then the counter changes to 2, a sub 2, a sub 3, a sub 4, a sub 5, until you get to the last term of your partial sum, whatever n happens to be. It might be 10 or 12 or something like that. So then if you had 12 here, you'd have 12 terms being added together. Is that clear to everybody? Okay. This is general. This would pertain to any type of sequence that you're forming a series with, where you're adding that group of terms together. So this would be the general description of n terms being added together of any sequence. However, for this arithmetic pattern, then this a sub k right here, a sub k, then becomes this described value. And again, over here, I should put a k right there. Minus 1. So here's the kth term, which is this general description using a k here. And so that becomes that thing. And then I told you a little story about Gauss during the last session, adding the numbers from 1 to 100 together to help you sort of remember a story about how to come up with a formula for the partial sum. And it's the number of terms you have adding together divided by 2 times the first and last term added together. Okay, and you can look back at an example that we did on the previous video or in your notes. Okay, little light exposure to that. Now, let's talk about this other one, which is very important, called a geometric sequence and series. And we'll start by talking about the geometric pattern. Let's see. Why don't we start with some starting value, like we did an example previously, and so we can sort of determine what we see as a pattern, and then see if we can generalize it from the pattern. Okay? So somebody give me a number to start with. 6. Okay, very exciting. Okay. Okay, so we're going to start. That's okay. Our first term is a 6. Okay. Now what we want to do to form this thing called a geometric pattern is I want to multiply that initial value by something. So let's say I multiply it by, how about a half? Multiply it by a half. Okay. Okay, now remember back in the discussion on exponential functions? How did I describe the way exponential functions grow or decay? As a multiple of the base, okay, as a multiple of the base. Now think of what we have going on here. We're starting with a value of 6, and we're going to be multiplying by a half to get to our next term.
3.
Okay, very good. 3, okay? Half times 6 is 3, good. So what I'm going to look at here is my pattern. So my first term is equal to a 6. My next term is going to be equal to 6 times this 1/2, which we know I'm just going to go over here and put a 3. And notice I left some space. And now I'm going to go for my third term. And so I'm going to take that previous result now, which is 6 times 1/2, and I'm going to multiply that result by another half. See, I'm showing the detail. And so what I've got is 6 times 1/2. Let me tuck it in here. I have a 6 times 1/2 raised to the 2 power. And then that result is going to be equal to 3 times a half, which is 3 halves for the final value. I'm not as concerned about the final value as I am looking at this pattern that I'm seeing here. How many of you see the pattern? One person sees the pattern? Oh, that's good. More hands went up. I like that. Okay, let's go to the fourth term. We have 6 times the half times another half, right? And so we're ending up with 6 times a half to the 3rd power, and then that's going to be a half of this value, right? Which would be 3/4. Okay? So our sequence we have, this geometric sequence, is going to be made up of a set starting with, 6, our first term, and then a 3, and then a 3 halves, and then a 3/4, and keeps on going in that fashion. Feel good? Let's generalize it. So the nth term, you should be able to look at this pattern right here and see. It's this value 6 times our multiplier raised to, think of this as n. And notice the exponent there is one less than the term you're on. Right? Even back here. Look at this. 1 less than 1 is 0. Right? See it? Okay. So if you ever forget this, if you ever forget the formulas, but you understand what geometric means, then you can build yourself a simple example like we did to discover that the nth term is made up of the first term times the multiplier raised to the one less than the term you're on, right? One less than the term you're on. In general, this is called a sub 1, right? So the nth term in general is the first term's value times, and then what we do in this, instead of calling this like b for our base when we did exponentials, they go and change the symbols on us in the textbooks. We call this small r usually, small r. And so we call that r raised to the n minus 1. And so there's a formula for the nth term of a geometric sequence. And what r is called a common ratio. A common ratio. R is called a common ratio. Now think about what ratio is. It's a fraction that happens to be in common as you go from term to term. It's a comparison of one term to the previous term. So what if I took, and I wanted to look at this particular sequence. Let's say your textbook or an instructor gives you a sequence, and they ask you, is it arithmetic, or is it geometric, or neither? So what we could do is, if we wanted to see if it was arithmetic, we would take the difference between the terms. Remember what we called that d earlier? We called it the common difference, or slope, right? So if I took 3 and took away from it 6, I would have negative 3, and then I see if that exists between 3 halves and 3. 3 halves minus 3, no, that's not negative 3. So this would not be arithmetic because there's no common difference that exists between pairs of terms. But I want to see if there's a common ratio. So if I took the second term divided by the first term, I would have 3 over 6, which is a half, and I'd check that with another term. I might take the third term divided by the second term, 3 halves over 3, and I hope you guys are good with fractions, okay? This is a complex fraction, isn't it? Because there's a fraction built inside another fraction. And so what you typically do is play the invert and multiply game. But let me set you up for what comes later. The best way to clean up complex fractions is to think of each part, both the the overall numerator and denominator, as being each fractions, like this. Notice the common denominator of both those fractions is 2. So you multiply the numerator and denominator by 2, by the common denominator of all your fractions, and this method, if you remember this, will always clean up complex fractions, always. I think I maybe did something earlier in the course on this. And so you multiply top and bottom by the 2, and 3 halves times 2 is 3, and then down here 3 times 2 is 6, and we'd reduce that and we get 1/2. Oh, we have a common ratio existing. And we could go on and check the next pair, 3/4 divided by 3 halves. That would clean up to be a half also. So we have a common ratio in this problem, which happens to be a half. Any questions? Not too bad so far, is it?
Would cross multiplying work on this as well?
There's no cross multiplying going on.
No, but could you to find
No.
a common ratio?
No, that thing where they teach you that in beginning algebra, basic algebra, cross multiplying, that's when you have an equation, like proportions, two fractions or proportions equal to each other. Like for instance, what if I said x is to 5 as 9 is to 15? In beginning algebra, they teach you that. They say cross multiply. Now, what's actually the better way to and then you're going to get 15x equals 45, right? And then divide by 15 and get your answer. The best way to do these is this. See, this is a fractional equation, and multiply both sides by the common denominator, which is 15. Multiply both sides of the equation by your 15. And that cleans it up and immediately gives you 3x equals 9, and then x equals 3. Right? Okay. So cross multiply goes back to the beginning basic algebra thing, and it's only when you have an equation. We don't have really a complete equation here because we have two unknowns sitting here. So what we do is we take the ratio of these values and we reduce it. The ratio of values and reduce it, and notice that they are in common.
Not to be argumentative, but if you look at the 3/2 and the 3/4, and you cross multiply 2 times 3 on your sequence up there, that's 6. 3 times 4 equals 12. That's 1/2.
Yeah, but there's no equal signs here. See, cross multiplying is something they taught you in proportion when you have an equation. When you have an equation. And they teach you that, and in reality, what you're doing is you're multiplying both sides by 15, and you're also multiplying both sides by 5.
Right, I'm just pointing out the pattern in that sequence.
Yeah, but you're not going to see your half.
Yeah, you do.
How do you
2
how
times
do you
3
see?
is 6. 3 times 4 is 12. That's 1/2. 3 times 2 is 6.
If you do the juggling properly.
Yeah, well, it's straight across. 3 times 2 is 6. Look at 6.
Right here?
Yeah, go to
Yeah.
the second number to 3.
Oh, here?
Yes, 3
Yeah.
times 2 is 6. 3 over 6 is 1/2. 2 times 3 over 3/4 is 6. 3 times 4 is 12. 1/2.
Okay. Okay.
That's what I was asking. Will that give you that pattern?
If you mentally play the game the way you just did and do that consistently with one problem and another problem, what you're thinking, I think, is correct, but that's not the safe way to approach it. The safest way to approach it is take one term and divide it by the previous term, as I've shown here, and demonstrate that that happens to be common. You result in a common ratio between terms. Okay? Good. Now, if you had started with some other base, like let's say the base was 2 instead of 1/2. If the base here, or this common ratio, was 2, then what's going to happen to our sequence? It would be going from 6 to 12. If we had an R of 2, and our first term was a 6, then our geometric sequence would be 6, 12, 24, 48, and notice how you're doubling. Your common ratio is 2. Your common ratio is 2. You'd be doubling. Does this thing head towards 0? Obviously not. It's blowing up on you, isn't it? This sequence is blowing up on you. Okay, unbounded. All right. What's happening to the nth term in this original one? What's happening to the nth term as n gets larger and larger and larger? We started at 6. We went to 3, to 3/2, to 3/4. Where's that heading? It's heading towards 0, isn't it? Aiming towards 0. Yeah. Very good. Melissa observed that if this common ratio is less than 1, then as n goes larger and larger and larger on you, you're heading towards a limit of 0 for your nth term as n goes towards infinity.
So
Okay.
it's basically exactly like an exponential, only you only have terms.
Yeah. Yeah, and as I've said, textbooks don't say that. But why not tie this back to something that you're more comfortable with after all that studying you've done with exponential behavior?